Всем привет! Меня зовут Павел Топорков. И сегодня я хочу вам рассказать про
Hi,
oPWNstack.
name is Pavel Toporkov, and we will be talking about oPWNstack today.
Все должно быть понятно.
My presentation is designed for people who have not had previous training, so it should not be too difficult. Now, if you see something that doesn't make sense, then it is by default. It is by design.
И мало времени, поэтому будет немножко скомканно. За это я прошу.
I have little time, a lot of stuff to deliver, so it may be confusing. I'm sorry about that.
Поэтому сделал свое собственное облако.
So OpenStack is an open source cloud computing infrastructure.
Google Cloud, Azure.
I guess many of you guys must have used Azure, Amazon, or Google Cloud. And OpenStack enables you to do pretty much the same things that, cloud providers do, but off your own infrastructure.
Я вот зашел к ним на сайт.
Lots of companies are using OpenStack.
Я знаю.
I'm showing some of them here. At least these are the names I recognize, but naturally there are many more others. I don't really know why I'm showing this. Maybe I just want to prove that OpenStack is important. OpenStack has got a pretty simple architecture. I'm not going to explain this. So simple it is. Actually, the old schematic is old. The new one in front of you is, much more comprehensive. And every word you see corresponds to a particular module of OpenStack. It's a modular system, you guessed that. So you can pick and choose and combine what you need. OpenStack core or kernel has over 12 million lines of code in Python. For some reason, they take pride in it. Search me why. They've got over 900 Git repositories. They also have lots and lots of external dependencies on various binaries and hardware. And on top of that, they add the multi-tenant model, which makes it even more fun. Which means that OpenStack is very difficult to deploy.
Прежде чем мы перейдем к какой-то технической части, я хочу выразить большую благодарность.
Before we get technical, I want to thank people from VK Cloud for having their cloud on OpenStack and for putting up with me. Because, I kept having fun with their OpenStack. They actually paid me some money as part of their bug bounty program. So what I will be delivering now is based on my own bug bounty experience around OpenStack. When you start researching something new, you gotta identify the attack surface. That is the areas you may want to attack. Shown here are all the APIs related to this or that module. OpenStack has been around for a long time. So I'm guessing that all these APIs must have been checked and researched many times. So maybe it makes a little sense for me to explore them. That's why I decided to focus on a single module, and I chose Trove. Trove enables creation of managed databases in OpenStack. So in your web interface, you can choose that you want to have MongoDB, Postgres with such and such capacity, such and such architecture, single node or whatever, and then you will be able to back it up. All this is done in web interface. It's actually very, very convenient. This is how Trove works. There is Horizon Dashboard, which is, shall I say, our web interface, which talks to Trove API, Trust API, in fact, which maintains some records in the database. But much more importantly, it will be talking to RabbitMQ message bus, and under the hood, it will create a virtual machine where our database will be running, and it will also be talking to the same message bus. Now, this bus is required for us to send commands to the virtual machine from the web interface or collect metrics. For example, you indicate that you want to do a backup of your database. This message goes to the bus, and then the agent running on this virtual machine receives this message, does the backup, or does reconfiguration of the database if this is what you want, and also keeps sending metrics to the bus so that you can see the actual load ratio of the database.
то мы
If we drill deeper,
снизу доклад
we will see the following.
на каком-то конференции про OpenStack, и там они говорят, что
Now, the link will take you to an OpenStack conference report.
вот эта шина, она общая для всех тенантов. То есть
where they say that this bus is shared across all tenants. So all clients of a given cloud will be using it, which is not secure usually. However, they create a separate account. In fact, not for every client, but for every instance of the database. Also, they create a separate queue, and this account will have only access to that queue. And another layer of protection is that they create a key to encrypt all the messages that will be going there. We see they have symmetric encryption. But do note one very important slide in this word in this slide, which is that all the messages sent to the bus are serialized. Serialization is so much fun. So we have a class of serializable notifications. During deserialization, the system tries to extract from the serialized object, which is JSON in our case, notification classes. And then it needs to discern what's related to a particular class, what's related to the packet, then does the imports, then create an instance with context and all the other fields of that particular object. The interesting thing is that calling a function and instantiating an object are pretty much the same function, which can be exploited, because both are callable objects in Python. So we need to find a class or a function which is already available in the existing code of OpenStack, which ignores
допустимо для нас использовать первый аргумент, потому что на контекст мы не взаимодействуем. Контекст в данном случае это просто...
Or, legitimately, or, uses the first object, which would be dictionary in Python context. In the way that's fine by us, with some query arguments.
Ну, в общем, контекст вызова в целом понятно.
Okay, you see, I guess you see what I mean. So we need to have a function that has the right call context.
Чтобы мы хотим найти такую функцию, которая проигнорирует первый аргумент.
So we're looking for a function that will ignore argument 1.
Именованный аргумент она бы использовала так, чтобы мы могли получить выполнение кода.
And that can, use at least one argument it runs with in a way that works for us. And this is what I found. So a module called Oslo Concurrency, which is also a development which is part of OpenStack, it has an execute function as part of process utils. So it's positional arguments. It expects a command. And then it sort of attaches it to a string, I think, right? The problem is that we cannot send our payload with this command. However, there are two named parameters. One is run as root, which can be set to true, and then OpenStack will try running this command with root rights. There are different options, however, and there is root helper parameter that will add a prefix to a command that we're trying to execute. So for some legitimate situation, for example, it should have sudo, but we can actually play with root helper, can't we? So this gives us the following exploit chain. So we obtain account credential encryption keys from that particular Trove instance one way or another. In my case, it was pretty easy. I could see a virtual drive that would connect to the database. Then I would reconnect to a different virtual machine. I would dump the creds and the keys. And then with these creds and these keys, I would connect to Rabbit. Then I would send this object, having encrypted it with my keys. These are the takeaways. In clouds, in fact, in this large project, generally speaking, the attack surface is not limited to externally accessible APIs, the usual suspects, so to speak. So the agent running on a virtual machine can also be part of the attack surface.
Интересных мест, которые можно еще рассматривать как по версии атаки, их может быть больше.
And I'm guessing that there are potentially lots of others similar attack surfaces. Then I wanted to report it to OpenStack, and they told me we won't fix it. They told me as an OpenStack user, I should not have access to the database hard drive. Like they are not responsible for me, misbehaving. And who am I to argue with them? So I decided to forget about it. But I kind of kept thinking about it. I decided they won't fix it because they believe that managed services are safe. So they are expecting me to never be able to get access to their drives. So they seem to believe that their managed services are impenetrable. And they do have lots of managed services, and I only have that many hours a day. They have 3. So I decided to find whatever these managed services have in common. And it turned out to be that section, this module called Neutron. Neutron is a virtual, maybe not necessarily virtual network realization on OpenStack. They can support both virtual and non-virtual. It is a shared module because all the entities we create in OpenStack, they need to be connected to your network, because otherwise, why would you want to create them in the first place? And Neutron is as simple as OpenStack is. I think this is very easy to read or understand. That's why I skip it. If we start reading the data sheet, the first thing we will probably notice is port security. It is a mechanism in OpenStack virtual networks that will switch on and switch off security groups, which are effectively user rules applying to inbound and outbound traffic. And also, there are anti-spoofing rules maintainable there. In the OpenStack context, these are API tables, rules generated for every virtual machine that connects to the network at the time when it connects to the network. I mean, when you click your mouse indicating that you want to connect it to the network. So OpenStack knows which virtual machine it is, what kind of MAC address it has, what kind of IP address it's going to get. So then it does its mapping, showing, which MAC address packet should originate from, and if there is mismatch, they will be dropped. Now, if you switch port security off, which can be done if you analyze a provisioning map. So provisioning is what happens when you just start a new virtual machine. So in this flowchart, we're particularly interested in that little block on the right. What does it show?
Neutron, собственно, как и, наверное, мы могли встречать на Амазоне или на других облаках.
Neutron, just like Amazon or others, provides metadata service. With Neutron, that's the IP address where it's available. Actually, very similar to Amazon's. So it enables the virtual machine to obtain data about itself, if for some reason it needs it.
Виртуалка может получить, допустим, данные о своих публиках, которые нужно положить в
can also obtain this way data on its public keys.
И вот это уже для нас очень полезно.
And this is extremely important and useful.
Мы просто выключаем port security.
So if we disable port security, so anti-spoofing no longer is running. And from that moment on, we can launch any network attacks against a virtual machine. So with this network where port security is not running, we can create our own extremely fast DHCP server. It doesn't have to be extremely fast, by the way. It can, it can give out just a single address. All it's got to do is do it faster than the OpenStack server. Then we create some managed service in the same network. And upon the first start of this managed service, it will talk to metadata service to collect the keys. Well, it's a managed service, so it will contain the keys of the tech staff of the cloud service provider, so that if we have issues, they should be able to connect to our system and help us resolve those issues. However, now that we're spoofing DHCP responses, upon the start of the virtual machine, we should be able to route the traffic through our instance. And then we should be able to provide our own keys, and then we will connect over SSH. What are the takeaways here? Managed does not equal secure. Managed services may contain vulnerabilities. Now, the solution I've shown may be seen as primitive. Please note that it can be used in the context of network attacks, but in other contexts as well. So a managed service is, well, a service running off an image of software developed by somebody, and there can be errors and vulnerabilities at every stage. Network attacks can also be used in cloud infrastructures. We shouldn't really idealize cloud infra. This should be the most interesting part. I've been thinking about the name, and that's what I focused on eventually, and I hope it will be clear why I chose this particular name. As I've been studying Neutron, I identified this pretty interesting field in the config file called extra DHCP opts, which gave me a sense of deja vu. So it turned out that it enables switching on some additional DHCP config options. The more I read about it, the more familiar it felt. Then I checked out this Neutron schema, and then it clicked for me. I realized that Neutron was using DNS mask as its own DHCP server. And DNSMask has this option of a DHCP ops file, which enables people to maintain a file that will list all DHCP options. And it's like a little database of DHCP options. The DNSMask shown below is what it looks like on OpenStack when you create a VM. Note that all these options have a tag in front of them, so these options are tagged, and we need this tag in order to identify which VM should be given which options. That's how it works, more or less.
И выставлять какие-то свои DHCP-опции. Допустим, вот тут на примере мы пытаемся выставить тест.
We can maintain our own DHCP options. For example, for a test, we can have a value of val, and it won't work because there is no option like this, but I needed to choose something as an example. This leads to a very simple, childish vulnerability. We cannot use just anything in the field name because this list is limited, but the value field can be filled in arbitrary manner. So in this extra DHCP ops file, we can easily add our own entities if we so choose. How can you exploit that? Well, we can reconfigure our own newly created network and then push our own DHCP options to our own virtual machine. Not entirely clear why we would want to do that, though. little fun. Secondly, there is this concept of external networks on OpenStack. This could be, for example, internet-facing networks that have public IP addresses, and they're usually shared across several tenants. However, in networks like this, we're not allowed to switch port security off. So if we camouflage ourselves as a router, then port security will limit our traffic before it reaches us. We can operate our own DNS server, but like I said, there will be loads of tenants using this network, and this won't be ethical. To provide, people running their production systems with our own DNS servers. So I decided to run a fuzzer. Remember, I said bravery and stupidity. Who else would do that in 2021? So in about 2 hours, my fuzzer gave me this single crash for DNS mask. I was only fuzzing the function that parses DHCP opt file. See what's happening here. Initially, the parser calculates the number of colons in the strings that we send. Why would we do that? Well, because the option can be a MAC address, for example, and it tries to keep its MAC addresses as a bunch of bytes in memory. That requires parses hexes separated with commas. I'm sorry, with colons. So it tries calculating the number of colons, then it allocates as much memory plus 1, and then it parses hexes there using the parse hex function. The parse hex function, in its turn, will run until the first invalid symbol, something that doesn't really match the mask of colon and blank. So we allocate a fixed amount of space, but then it parses until the very end, which does create an obvious buffer overflow vulnerability. Now, for people like me, spending more time on burp than with buffer overflow, a mild reminder is that buffer overflow is almost as awesome as CSS. In order to exploit buffer overflow, we need to understand how memory inside DNS mask works. All the directives that we can send with our config are stored as DHCP opt structures. These structures have pointers to content, that's a val, and content links, and a pointer to the next structure of the same type, which means that they are stored as a linked list. And that's an example. So there's DHCP opt1 with the data 1, there is length, there is val, there is a next, which is DHCP opt2. How can this be exploited? If we do overflow of the data 1, then we will be able to override the DHCP opt2 with whatever. And this way we can do arbitrary memory read. It's not that simple, however. File parsing is done string by string, top to bottom. No, top down. We cannot do a buffer overflow if this buffer has been allocated for the previous directive. We can only do the overflow for the current iteration. As we overflow data 1, we won't get much. That's not much of a challenge, however. As long as we know how libc allocators work. So when we free memory up to return it back to the allocator, rather than sending it back to the memory heap, it will first put memory into buckets. There are fuzz bins, and they are stored as a list, And every bin or every bucket will collect chunks of the same size.
И, собственно, вот этот fuzz bin он применим для маленьких чанков памяти. То есть, когда мы...
So this fuzz bin applies to small chunks of memory.
x70, оно пойдет в fuzz bin. Если мы...
For example, you allocate 0x70, it goes there. If you allocate millions of megabytes, then it won't go to fuzz bin. There is another kind of bin, which is unsorted bin. Now, this is a structure designed for large chunks, and it's stored as a as a geo-link list. Now, these are liquid goods for the allocator, and sometimes they need to be combined. So since you have this geo-linked list, this is possible. And that's why you reduce fragmentation of available memory. Now the idea is like this. So we have identified a chunk in memory, chunk 1. Then, and it's a small chunk. Maybe it doesn't matter that much, but in any case. Then we free up another chunk. In the context of DNS mask, what we can do is give it an invalid option. So it will parse it and free memory up. And then we give it another memory chunk, which is bigger than the previous one. Doesn't have to be huge. So the idea is that chunk 2 needs to stay in fuzz bin. After chunk 3, we allocate chunk 4 of the same size as chunk 2. And then, as we parse it, we can do overflow. And then it will, as you can see, overflow into chunk 3. So that's the structure in the memory. Then we want to overflow data or override data 1. Then we reconfigure DNS mask with our options. So we want data 1 to be allocated after DHCP op2 has been allocated. Then as we overflow buffer of data 1, we will be able to overwrite len and vol sections, or values. After that, we request from that DNS mask the configs with the HTTP client. And then we're going to get the memory that we're going to refer to as the response. The problem, however, is what we're going to read. That's, again, not really that much of a challenge. This whole process I've just described, items 1, 2, 3, is pretty slow because we need to reconfigure DNS mask and it needs to restart. It's taking some time. So the usual techniques resulting in arbitrary leak, they take their precious times. Remember how allocator works. Let's add another step here. So after the data that we are trying to extract there, now with the help of data 1, we're overwriting some elements of DHCP op2, and after that, we want to have another huge free chunk so that it can be freed up after that. If this chunk is the first one and also the last one in the unsorted bin, then it will hold a pointer to unsorted bin, because it does need to have pointers. An unsorted bin exists in main arena, and it does have a fixed offset in libc. And if we are certain that this chunk is either the first one or the last one, it's pretty easy to assure that if we previously allocated lots of large chunks, this way we will know that in the unsorted bin, this will be the only chunk. Now we can guarantee that either or FD or BK or both will be pointing to unsorted bin. This way, knowing the main arena address, we should be able to calculate address for the libc. Note that we are not overwriting val. It's very convenient that the length field is before the val field. So we don't need to rewrite pointers to data 2. We don't know their addresses. Because we don't need them. Now, when we can easily read it and we can easily grab the address to libc, time to pawn it. But I should also remind you how libc works. Allocated and free chunks look slightly differently. What they do have in common is that at the very beginning, they have chunk size and some flags. We don't care about flags today, so I won't even talk about them. If the chunk is allocated, if it contains some data, well, this data will be right after the size field. If it has been freed up, then at the very beginning of the data field, we'll have a pointer to the next chunk. In the fuzz bin, if this chunk belongs to the fuzz bin, or to the previous and the next chunks if it belongs in the unsorted bin. I will be talking here about Tcache exploitation, and Tcache is one of those bins belonging to the family of fuzz bins. It's super fast, and by default, it's the one to be used. So we have some data, and after it, we have, say, 2 free chunks. Imagine we're lucky that we have 2 free chunks there in the same Tcache. Now, if we can use this data to overwrite pointers, to the next element in the free chunk, and then we do 2 allocations. The first allocation from this Tcache will be allocated on top of free chunk 1, while the second one will be allocated using the address of deadbeef, the one that we previously proffered, so to speak. How can this be exploited? In libc, there is this great place in memory called free hook. This is a function that will be executed before you free memory up. What's good about that? So it's done with a pointer to memory that we want to free up. System, for example, is done with a pointer to the string that we want to execute. And it's an interesting coincidence, isn't it? So we can actually poison Tcache bin so that allocation happens on top of free hook. Then, when it happens, we will rewrite, we'll overwrite it with a pointer to system, and then we create invalid DHCP opt line, like the one I'm showing here, and then DNS will start parsing it. We'll say it's an invalid directive, and then it will try to free it up. But before it does that, it will do the system, which is exactly what we need, but not so fast. I was so inspired by this success that I failed to notice a very important thing. In the target server, libc version 2.17 was running, while Tcache was only introduced in version 2.26, which means that the server doesn't know of Tcache yet. So instead of Tcache, allocator is going to use fuzzbin. And before fuzzbin allocates a portion of memory, it will actually do the check of memory size using the length field at the very beginning. So this is an example of memory space around free hook. So if we have the length field there, fuzzbin will check it and will say, well, you're asking 0x30, but what I have here is 0x0, so I won't give it to you. It will go down in flames. I've been helped by talented people.
участок памяти называется...
There is this beautiful part of memory on libc, which is called mem-align hook. By default, it's available, so whenever we're compiling something, we can count on it being there.
Во-вторых, рядом с ним лежит malloc hook.
Next state, there is malloc hook. That's ostensibly the function that's gonna be triggered with every memory allocation.
Наверное, можно возразить, но вот этот 0.07f...
You may argue here that
это тоже не выглядит как валидный размер чанка.
That the stuff in the first line doesn't look like a valid chunk size. That's right,
другим смещением.
Unless you apply a different offset to it, like this. That's a different, I'm sorry, that's the same memory chunk with an offset. 07f is actually a very good match for a memory chunk sized 0x70. Well, junior elements should be ignored because they should be filled with flags, so 70 sounds just like right. Now, the idea of the exploit is like this. In our heap, we have some chunks from fuzbin. We allocate the first one.
Далее мы переполняем этот чанк так, чтобы перезаписать указатель.
Then we do overflow of this chunk so that we can overwrite pointers in the following chunk
Вот тут у меня как раз специально такой кривой
with pointers to memory address. Say it covers just a portion of mem-align hook. It doesn't sort of override it completely.
После этого мы аллоцируем два.
Then we allocate two chunks size 0x70.
Рядом с mem-align хуком.
You do remember it's a 0x7f. The first chunk will be allocated on top of the initial one, but the second one will go here.
Переписываем malloc hook.
After that, we overwrite malloc hook.
Будем вынуждены использовать ROP-цепочку.
Well, won't be able to use system, so we'll need to use ROP chain.
При любой следующей локации.
And with any further allocation, our ROP chain will be triggered.
Но
Everything seems to be fine, but not really. There is another issue.
вот этот конфиг DNS-маска, он генерирует.
This DNS mask config is generated using Python, and this config is generated in a text mode, which means that we should either be using valid Unicode or bytes from the range of 0 to 7f. And my ROP chain, and pretty much any ROP chain you can think of, will need to have pointers to a function that we want to call, some system function, for example.
И на payload, на команду, которую мы хотим вызвать. То есть
And the payload.
нужно указывать какие-то указатели. Не так просто сделать, чтобы указатель,
It's not that easy
который мы выделяем, состоял из байтов 00 от 0 до 7f.
to have pointers falling into that range.
Тут проблема, она достаточно техническая и решаемая, но я решил
It's a technical issue.
и сказал, а пусть SLR нам поможет.
It can be addressed. And then I decided, well, maybe ASLR can help me. ASLR often stands in the way. How about making it work for us for a change?
Это было плюс
So we decided to actually
И мы хотим
make sure the address of the controllable chunk should consist only of specific bytes.
положить указатель на систему, указатель на свой...
So want to put there pointers to system and our line of code.
Использую именно этот же чанк памяти только для того, чтобы...
I'm actually using the same chunk of memory here to keep this slide tidy, but it could be any other one, really,
Вот, и дальше.
as long as we know where it sits.
Malloc hook, у него старшие 24 бита всегда...
So this malloc hook
Ну, потому что вот так сложилось.
is sort of guaranteed to have its senior bits equal to 0007f.
Версия libc была чудесная.
Lowest 12 bits depend on the libc version.
Младшие 12 бит
My version
тоже были
was quite useful,
из...
and the lowest 2 bits were also fine for us.
Даже если бы не устраивало, то на самом деле можно было чуть-чуть там подобрать другое смещение,
Had they been different, I should have been able to find a slightly different offset,
которое рандомизируется
and
SLR.
it would work.
И
The remaining 28 bits are randomized by SLR, which means that they will be new every time a DNS mask is restarted. OPNstack is a production fail-safe, reputedly fail-safe solution.
перезапустят.
So if we down DNS mask, it should obviously restart it, shouldn't it?
Кликаем адрес.
So we can leak libc address, calculate the address of malloc hook, and get, with the offset that we have. If we don't like it, we crush the server. If we like it, we continue with the buffer overflow.
И да, я знаю, что это можно было сделать по-человечески.
Yes, I know.
Еще одну локацию.
It could have been done in a different way, with one more allocation for the payload, for the addresses we know.
Было гораздо дольше, чем я просто в цикле
But
запустил
you know what?
существующий эксплойт, добавил так.
Running my exploit in a cycle, making sure that whenever it delivers to the offset that I don't like, it will crash the system, was more fun.
Я зарепортил.
So I decided to report it to openstack. Well, this time they decided to take it seriously, and they awarded me with a CVE. And I think they were, quite fast in patching it. And then I decided to report it to DNS mask. And I learned that back in 2019, somebody else reported this bug, and it got fixed. But the commit said that it is not a security problem. That's why we're not going to push it in repositories. That's why DNS mask in repositories is still vulnerable. These are the takeaways.
Сторонние компоненты — это тоже в целом attack surface.
Third-party components are also an attack surface. You shouldn't be shouldn't be ashamed of fuzzing or testing well-known products like DNS mask, because bravery and stupidity can often help you find funny bugs. Thank you.
Привет, классный доклад, особенно то, как ты перешел от oPWNstack к
Thank you very much.
DNS маска.
Great report, and I really loved your transition from openstack to DNS mask exploitation. I understand that all you did was thanks to those weird options of Neutron. I understand that users should not have access to raw APIs. No, they are not raw APIs. Everything you click in the interface gets sent directly to openstack. So as a user of the openstack cloud, you are comparable to a system administrator. Do you actually get that kind of access? Well, DHCP settings are regular for sysadministrators. But it seems so easy.
Спасибо. Как всегда, супер крутой доклад.
Thank you. As usual, your presentation rocks. My question is
И вообще, как ты выбрал
sort of philosophical.
куска кода для исследования вначале?
How did you choose that particular section of code to analyze? Most of my life, I've been researching web vulnerabilities. Web vulnerabilities are primarily SQL injections. SQL injections are databases, and Trove is a database. Easy. It doesn't really matter what I chose. I told you about 3 vulnerabilities. There were many more.
Просто я вот из огромного списка тыкнул пальцем, выбрал.
Out of a long list,
Я знаком с базами данных. Я посмотрел.
I kind of blindly put my finger on something that I knew more about. I know more about databases.
Там получилось до более.
That's why I gave you this presentation.
Там еще один вопросик есть.
Question of there.
Спасибо большое, очень крутой доклад. У меня
Thank you very much. Great presentation. 2 questions.
верно ли, что DNS Mask все еще уязвим к этому?
Is it true that DNS mask is still vulnerable to such an overflow? It really depends on the repository. If you select it from master, it will be impervious.
Он был уязвим.
In the latest Ubuntu in 2021, it was vulnerable. I haven't checked it since then.
И второй вопрос.
So there is a chance we can still use it. Yep.
Мы заслали сериализованный объект через RabbitMQ.
So you mentioned this connection of unserialized objects through RabbitMQ. You lost me there. Can you remind me of the kill chain?
Используем то, что VK Cloud позволяет выгрузить.
I understand that VK Cloud allows you to download the full image of the managed database.
Что это часть атаки.
Что это как бы.
Well, OpenStack believes it's part of the attack.
Они у себя в документации.
I didn't think that way. In their documentation, they say this should never be allowed.
Именно схема атаки. То есть ты каким-то
Okay.
к вот этому API, который.
So you connected to this API that talked to RabbitMQ and sent an object there on behalf of the agent. No, I took creds. Then over Python, I connected to RabbitMQ. And access to RabbitMQ, is it available from any virtual machine in their cloud? Yes. And that's not seen as a vulnerability?
Нужны ключи шифрования. Ну, я считаю, что у тебя есть
Well,
разных пользователей у сайта. Ты же не считаешь это
you
уязвимостью?
do have lots of users on a website. Do you consider that a vulnerability? Most people don't. Thank you.
Еще вопросы?
Any questions?
Вопрос про версии DNS маска.
There was a question about DNS mask versions.
Еще были вопросы.
I forgot what the other questions were.
Почему Ну и тогда вопрос вот этому господину.
Why Trove? Okay, the gentleman who asked me about Trove.
Просто потому что я так захотел.
Why? It's just my whim.
Спасибо за внимание. И если будут еще...
Thank you very much. If you have any other questions, please locate me here.